So today we will talk about the Gödel's theorem. So the question is, can all the truths be provable? So let's start. So a long time ago, mathematicians had a dream to prove all the mathematical theorems from a set of axioms. And for example, at the beginning of the 20th century, there was even an attempt to build the foundations of math based on set theory axioms. This is one of the books which was written with a very respected group of mathematicians, Principia Mathematica. So the main goals of this book were to analyze to the greatest possible extent the ideas and methods of the math foundation and minimize the number of primitive notions, axioms, and inference rules. And what is, so for example, this is the page 86 of this book. It took 86 pages to prove that the 1 + 1 is equal to 2. You can see the like what was the idea of that book. But from another point of view, all the proofs were super rigorous and no room for misinterpretation. And the interesting part of the story that in the 30s, Kurt Gödel proved that the final goal of the mathematical formalists cannot be achieved. And he proved the theorem. The informal formulation of this theorem is that mathematics has unprovable statements. More formal formulation is that in any consistent mathematical system that is sufficiently powerful to determine the basic arithmetics of natural numbers, there are statements that can be neither proved nor disproved within that system. So this is one of the most striking theorems in the history of mathematics, and it has significantly influenced the development of philosophy of science and philosophy in general. And there is also a personal story about that. Over about 10 years, I've made several unsuccessful attempts to understand the theorem. And during the recent holidays, I found this YouTube video that made me believe that I've grasped the essence of the proof. And this is a picture of myself happy after I watched the video. So we will prove the Gödel's theorem now. And but before doing that, we probably need to understand what is the formal proof. What is that? So in essence, it's just a long chain of reasoning. So you start with axioms, then you have the rules of inference. You have a statement 1, statement 2, statement n, and then you have a theorem. It's just a string, nothing more. And for example, if you want to prove that 1 + 1 is equal to 2, just using the axioms of arithmetics and inference rules of logic, this is the proof. So in the beginning, you have the axiom, and in the end, you have the theorem. So you don't really need to understand the proof. What is important here is that S denotes the suspend operator. So S of 0 is 1, 2 times is 2. And as you can see on the right side is written that 1 + 1 is equal to 2. Again, it's not important, the proof itself. What is important that it's just a string, and you already get the idea that it's possible to validate by the algorithm that this is a proof. So the validity of the formal proof can be checked by a computer. That's the most important message which we should get from here. So there is an algorithm. So this part isn't obvious, but now we'll make a super unobvious consequence from this fact. The point is that there exists an algorithm that prints all proofs in the world and nothing else. Let's call it a super prover. This is a super prover. It's a very nice algorithm, and let's see how does it work. So it just takes the smallest possible string A, and then it checks is it a proof or not. So we understand that we can check whether anything is a proof or not. So there are formal rules. It's just easier. So it understands, okay, it's not a proof. Then it takes the next string. It's not a proof, etc. So it just takes all the strings in the lexicographical order and checks all of them. And then at a certain moment, it can meet, for example, this string, which is a proof that 1 + 1 is equal to 2. Then the algorithm says, okay, I know the axioms, I know the rules of inference, like how to derive the stuff. So I understand that it's a valid proof, and it prints it, and so on. So in principle, it will print all the proofs in the world, but it will take a lot of time. And that's a first step. And this is one of the most important ingredients to prove the Gödel's theorem. So if we suppose that the Gödel's theorem is wrong, then what does it mean? It means that all the truths are provable. So because the Gödel theorem says that there are more truths than provable stuff. So if it is wrong, that means that all truths are provable. So it means that this our algorithm super prover will actually print not only all the proofs, but it will print all the truths and nothing else. Yeah. So we assume that Gödel's theorem is wrong. It means that this algorithm will print all the truths in the world. Then we will immediately get the contradiction, and we will see it on the next slide, the contradiction. That's the idea of the proof. So this is the last slide. So let's try to concentrate on the last slide. So how we get this last contradiction? We will just remind you what is the algorithm by itself. So so the algorithms, they take an input string and they convert it to an output string. That's basically the mathematical definition of algorithm. And each algorithm is represented by its source code. So let's think about the C++ language, for example. In essence, algorithm is just a text and nothing more. And for example, what we can do, we can take the smallest ever C++ source code file, like and call it A1. And this will be the smallest one. And I do not really know what is the smallest C++ program, but let's just imagine that if you enter 1 to the input, it will hang or it will not halt. So we can imagine that some algorithms, they just halt, right? For example, they always try to add 1 and never print anything. So they can either print something or halt. Imagine we print for 2, it returns 3. Sometimes it may return some characters. For 100, it returns these strings. Then there is a second algorithm. It's the next one in the lexicographical order. So it has its own values it returns, and so on. So we can really list all the algorithms of the world in this list, because algorithms are nothing more than just a text, and we can order them in the lexicographical order. We start from the smallest one and we finish with and then we continue. And this is the 100th algorithm. So you see, sometimes they do hang, they do not halt. It is represented by these red arrows, and so on. And now is the most important thing. So we just suppose that this super prover algorithm, which we had in our previous slide, it can print all the truths in the world and nothing else. So now we will just use these super prover algorithms to construct our new algorithm, which we'll call the diagonal spoiler. So this will be our new algorithm. So the only thing that it will do, it will just concentrate on this diagonal part of this table. So so what it will do, for example, to understand what will be the result of 1. So it will just take a look how the algorithm A1 behave with the number 1. It will understand, okay, I have a super prover on my hand. I understand all the truths in the world. I can also understand what will be the output of A1. I understand that it hangs. Okay, then said it hangs, then it will just type here some character. Doesn't really matter. For example, star. Okay, if it hangs, it's star. Then for the 2, it takes the algorithm A2, and it sees that if you apply to the character 2, you get T. We also spoil it. We write here not T, but T star. Whatever we do, we just need to spoil it, and so on. We spoil for 3. We spoil it again. We get 1 star, etc. So and so for every single entry, we just spoil the output. And if we see that it hangs, and we can see it because we have this super prover which knows all the truths in the world, then we just put a star. And that's basically the whole, because this diagonal spoiler is constructed in such a way that it is definitely not the first algorithm, because it has a different output on the first place. It is definitely not the second algorithm, because it is different here. It's not the third one. So whichever number you take, it's not that one. So basically, this diagonal spoiler is not here in this table, and that's wrong. Like this table has all the algorithms in the world. That's a contradiction. So that's the proof. So let's just grasp again. So what we just did. So diagonal spoiler can be found in the list of algorithms. So again, so what we did in the beginning, we supposed that the Gödel's theorem is wrong. Then after that, we understood that it means that all the truths are provable. Then after that, we realized that if it is true, then we will have this super prover algorithm which will print all the truths and nothing else. After that, we realized that using this super prover, we will be able to construct a very special algorithm, the diagonal spoiler, which will not be in the list of the all algorithms. It's obviously a contradiction. So this diagonal spoiler is not in the list of algorithms. It's a contradiction. So it means that the Gödel's theorem is true. Yeah, that's all. Thank you.